I am live. What? Here we go, people. Hello. Oh, wait. I need to update my doc here. All right. Hello, everyone. Hey, Dutch. Hey, Johnny. Hey, Jumbo. So, please don't spoil. I still didn't watch the most recent. What's the series name? It ends with us. No, what's all this? All no, not it ends with us. What's the? The Last of Us, yeah. I didn't watch the last episode yet. I was working all day long. Hello, Sonic. Hey, Christian. Hey, Myland. Hey, M40K. You have been all intrigued by this image here, and this is this is rendered with 32-bit integers, no floating point operations, or at least a little bit of. Hey, Alexander. Yeah, you can see the artifacts here. These are the artifacts of 16-bit mantissa, not mantissa like fractional part resolution here. Yes, 1660. And it's terrible because I tell you what the biggest problem is with that. You can't, like, if you want to calculate the length, you have to add up the squares. So the highest number in one dimension can be like 128, because if you multiply like 256 or whatever, it's already out of range for 16 bits there. And yeah, that was the biggest problem. And finding a fast square root was the other one. Need double the bits? Yeah. Probably. I'm thinking it might be in some at some points, stages in the code, it might be useful to have a higher resolution. There is like spoilers will result in a permaban here. What? Oh yeah. Last of Us, Dutch. We switched the topic long time ago. You need to fast forward the stream. Anyways, yeah, this is the shadows didn't work at all. I tell you that the accuracy in the lower, like, I don't know, steep angles, like here, the shadow cast here, that was like, this is broken. And it was broken here. On the plane, it's alright. But like close to round edges, it's quite broken usually. Anyways, renders fast. By the way, bit shift to take square root. Oh wait, the resolution is too high. It calculates a higher resolution here. How that? What is your... Need the horizon? The glitches, you mean like the... yeah, we will see in a second. Raymarching fixed point. Here we go, this is the code. Need to reduce this... Okay, we can do... 320 by, what is it, 360, 180, it's 16 to 9. The artifacts, yeah, here, if you look closely, this is just at some point it reaches the maximum step count here, and since the steps are like really, we can add some fog. Fog is easy to calculate since we have like the distance. So actually we can make it more realistic, not so clean. I said I was, so since last Monday where I streamed, not everyone was there. The plan was to do, wait, this is the one, yeah, wait, this is with tasks, yeah. This is how it renders if I split up the rendering to tasks, and because the light source is in the center. This is what we did last time, like to make this distributed and split up the ray tracing. Blenders, yeah, no. And this is how it's done. It's done. wait. Let me be clear. Look at this icon. Done. This is when we don't do a distributed render. So the distributed render is very not performant. I checked. It's like with this performance testing of Chrome, very bad. And I was telling you bullshit last time when I mentioned what my plan is, like to we have like the primary rays, then secondary rays, shadow rays, and so on. And I wanted to only outsource. Hey, Grausteif. And I wanted to outsource to the MCUs only the stepping task, because I thought, oh, hey, there is no complicated math involved, only multiplications and additions and subtractions and so on. That was total BS. I have to do a square root each step. This is no good. Yeah, I'm calculating the distance. The distance always uses a square root. Oh man. bitluni, yes. Yeah, that's 0% Radler. So, splitting up the tasks, or like calculating a pixel into individual tracing segments, doesn't make sense, and it makes it really slow. So what I figured, since I need square root anyways, I need to implement a fast square root for integer fixed point arithmetics. And this is, I found a source which is not working. I tried so many methods. Oh no, I think where is it? He's wonky. Yeah, so what? Wait, I didn't save that. Let me check if I can find the tab. Here. This is the tab that I found from 2019. Someone is trying to do also fixed point math on an ARM core. And yeah, there's the Newton method. That's what we doing as well. And then we have this friendly person who does a lot of math, and this is like square root, like it was done on Cray. Some history there here, I think. Yeah, it's an approximation. It's interesting because I didn't know how that works, but I came to the same solution in the end. I tell you, here's the lookup table for the starting point of the approximation. So the Newton method, if you don't know, is like it checks one point and tests it. Oh yeah, we are too high or too low, whatever, and then goes in the different direction using the derivative and so on. So it tries to find the actual target with some iterations. They use also bit shift, yeah. But I tried this solution, didn't work. There is like an I commented it. I don't know what happened to my comment. It's not showing. Strange. I commented. Yeah, my comment is gone. I don't know. Maybe it's not approved or whatever. I also added a comment here. I don't know what's happening. Why is it not showing? Let me update. Maybe it's there. Oh yeah, here. Found the issue here. We look up the table and then we shift left the result. Doesn't make sense. It wasn't toxic enough for Stack Overflow. Yeah, so yeah, that must be a mistake, because why would you shift something that's from a lookup table and losing 22 bits of precision there, especially since all the values are like more than 10 bits. So doesn't make sense. There is like some error in there. But I made this one here. So I tested different methods, and my approximation method, let me get this here. Where's my, this is what I came up, and it's actually, I'm doing the same thing in the end, like they did. I started with Newton method, two steps of the Newton method, but yeah, and used a table that I calculated up front. The table is calculated from the exact value that I would expect between 1 and 4. And I tell you why. This is a quite interesting mathematical. I don't know. I'm like totally in the bubble right now. So I will paint it here. Oh no. Yeah, I can do here this. So we have like 16 bits fractional and integer part. So this is like 16 and this is like 16. And I used the Newton method like with the value 1. So this is just a 1 in a fixed point arithmetic as a starting point. And the approximation, like after 2 iterations, was great with the Newton method when you started with 1. But it was like terrible if the value was below 1. So if we have like x is smaller than 1, then the result of inverse square root gets higher and higher because there is a division. So we have like 1 divided by square root of x. So this, if the square root gets small, then this value gets even smaller. The deviation is, or like if this value gets big, then it vice versa. I can show you the results in the calculations. It's a little bit all over the place. I made a graph. So where is it? Here we go. So yeah, so I made, with the help of ChatGPT, did basically the rendering of the results. So this is with logarithmic scale. This is like the square root reciprocal is looking like. Let me remove that TTS stuff. Okay, so this is the approximation. This is the actual is beneath that. It's exactly spot on, and this is the relative error, which is below 0.54% at most, and in the low values. If we don't, but this only if I use the right starting point for the Newton method. And what I figured is, all right, so how about if we have some initial value like 0.1 or 0.1, why don't we normalize it or like multiply, shift it with integer shift? Hey Artem, integer shift, so it's between 1 and 4. Why 4? I will tell you. This is crazy math. So we can shift it to the right by an even amount of bits. Not an So this is so crazy because we can do. Let me draw it. The math is like that. 1 divided x, and then let's say times 2n equals I think, what was it? 1 square root x, and then it is, I think, divided, 2. So we can pull that out by shifting. Oh no, you can't see. Shit. We can just pull it out by shifting n by 1. So what we can do, we can calculate, like we can multiply it by a power of 2 that's even in the beginning, and then after the fact we can half that, like shift it back but 1 less. I can explain it very well, but I can show it what we do here. All right, so this is what it happens. This is like the naive implementation. So if it's below 1, we just multiply it by 4, and this is our n, incremented by 2. If it's bigger than 4, so we have like a nice starting region of between 1 and 4. We basically shift in the other direction. Foo! It's not running on the cluster yet. It's all simulated. Now we need to put it on the microcontroller and then on the cluster. We will test the microcontroller and over serial, like communication today. This is the goal. But I will explain the math. Yeah, and then we have our. This is how I started. Then we have our iterations. So I have a starting initial guess is basically the precise inverse square root of that value between 1 and 4 that we take like from the table size. And because of our 16-bit precision in the fractional part, the table size bigger than 16 does nothing to the precision. The precision is lost because of the 16-bit, lower 16-bit. Anyways, this is the implementation, and then after, in the end, we just shift I by 1, and then multiply it again, we're done. This is how it works. Yeah, so that's normalizing and denormalizing again. And then we have a nice initial guess from the table, but we could use also 1. I don't know, wait, we can check that. This is like my initial approach. Wait. I tested a few things here. Yeah, here, so for reverse square root, because this working with fixed, this one is working just with regular float even, I think, yeah. So let me calculate that. Yeah, so very low. The deviation is super low. And we could even, I think, in that case, we could even just use, wait, where is it? Not use the table at all, just using 1 in that case. Because, but then we would like need 1 more iteration or something. Oh, yeah, that's bad. So it's good in the beginning, but then it gets worse and worse. So let's try 2. Oh, wait. Oh, this doesn't work. 0.5. So actually we need a good value there. So the table, yeah, no. Anyways, the table is necessary as it seems. But I took a look again at that one. Where is it? Where is the Stack Overflow? Here. Okay, so I took a look again and what they even do, they even use higher precision by keeping the, since the integer part in the end is only between 1 and 4, they do exactly the same thing. So there is even like an assembly, like an opcode for trailing zeros that you can use to basically find out the amount of bits that you need to shift. And they do like, this is a binary search intrinsic if the opcode isn't available. So RISC V lacks, I think, this opcode, so we would need like to use this implementation. And yeah, they are basically normalizing it, but not to our 1616, but like to 3 or 2 and then 30. So they're using way bigger fractional part, but still doesn't work. So I don't know what the issue there is, but it's quite interesting that I derived basically the same or a similar method to them, maybe inspired a little bit to use a lookup table as an initial value, but normalizing the starting point to have like the table confined to a specific range is quite cool. So this method didn't work. Then we have some other suggestions here. This method here just checks if the value is below 1. If yes, it returns 1. So it doesn't calculate fractions, square roots of fractions. So that's also my explanation that I replied, because yeah, it doesn't work. Newton method falls apart if you have like a wrong starting value, especially in the for like x smaller than 1. So I thought, okay, what do we do? Hey, 404. How much did you miss? Oh, you can watch in 2 times. It's only like 20 minutes. You can watch in 2 times speed from the beginning, because I explained everything that I did with the fixed point math since Monday. So I was trying to find basically an inverse square root. Yeah, here this dude uses division in the end. So to avoid this division, we really need to use like this Newton method of basically this term. And if you look at this term, here, you will find it also here. Huh? Newton-Raphson? First iteration, second iteration? That looks familiar. That's the fast square root that's used in Quake by John Carmack. Was it Carmack who wrote that? All right. So it's also approximating with the Newton method. The only thing that's magic here, we have like also x half, which is also basically here, I think divided by 2, because then, yeah, 3 halves, and then this is halved, so you have x half times that. So you just rewrite that and you get basically 3 halves here, and then you have x half here. And that's basically this approximation stuff. Then we have this magic number, and the article, bit operations. Yeah, that's the interesting part. So what's happening in here is the representation of floating point. I think it's explained as well here. Here, this is the representation of the floating point value. You have the exponent here, and basically the mantissa here, where 1 leading 1 is basically assumed, and the sign is here. And what the magic number is doing, I read the article, and it's quite interesting. It's doing basically the logarithm. Wait, where is it? Magic number. All right. Let's see. No. That's actual math that's happening there. Where was it? It's quite like this. What's the sigma? What's the name of this Greek letter? Here we go. I think aliasing. Okay, so this is the interesting part. I will lose you if I go further into details. So if you look at the logarithm, base is irrelevant, then you can pull out basically minus half. Wait, where's the how do they call it? Identity. So basically, yeah, there is also the missing 1 plus mx is basically mx plus sigma, and the 1 is missing in the mantissa. So it's magic is happening there, and basically calculating the value. It's not the only magic number. The magic number changed a few times, or different people calculated a different magic number, basically to make it more precise in the lower values or higher values or whatever. So what's happening here is basically an approximation of the starting value. The interesting part is also what we do yeah, what we do in the fixed point arithmetics, normalizing basically the mantissa, is already done in the floating point representation, because it's always, floating points are always normalized. We have the leading one that's not even stored, and then the mantissa is basically all the fractional part, and this is the exponent. So everything what's happening there, we did basically as well, except for this sigma, what it is here, this 1 plus as a starting number. So they can avoid using like a lookup table for the starting values. Anyways, yeah, so I tried that. I have one method that I implemented that was working well. If I show you, I tried different stuff. So where is it? Okay, this is changed back. I tried different implementations. So I also used a bigger mantissa. So I did also the normalizing. No, it's not working on the arrays already, because I had to figure out the fixed point math, including the inverse square root, to be ready to put it on the MCU. And this is the next step. I just want to explain what I did since Monday. So yeah, I did a second implementation that's basically using the leading zeros. Yeah, so the leading zeros to basically do the initial shift that we do. And yeah, also that's like the count. We just used the even number, and that's working out. And I used also, I think, 28 bits of precision fractional part. It didn't help. You know why? Because I converted back to fixed afterwards, and then the precision is lost again. So the imperfection, when I use here, or the lack of precision here, this is the implementation here, the lack of precision in this low value is basically, or here, is basically because the fractional part is truncated to only 16 bits in the end when it's stored. So either we use like an intermediate step, a different representation for fixed point math. Let's say if we calculate the square root or something, or we normalize a normal or something. In the end, we know the normal will be somewhere plus minus 1 for all the values. So there is a range where we are working around. We can maybe approximate that or whatever. I don't want to, like, if we would refine it more and more, we end up basically with an implementation of floating point. Like, so, yeah, this is the precision that I'm able to achieve with a 16 starting value lookup table, which is quite cool. That could be probably even cached on some MCUs. The precision is like 0.5% or something. In the worst case, like very small values, which would result like in big values outcome here. You can see like the lines are basically on top of each other. You can see the you can see, wait, I can, yeah, if I turn this off, you can see they're basically perfectly limping point. Also here, I mean, the value is so small. Here you can see there is a lack of basically fractional part. That's where it falls apart. So there is no, we can increase. Oh yeah, we can even test it. So I can prove it to you by just let's do like 32, and then this was, what was the value here? 0.004, so 4%, and this is only like a little bit improvement like here, but the biggest value is still the same. So there we can, even if we make it like really big or whatever, 128, it doesn't improve at all. There is only a slight improvement that really doesn't make sense. If we make it smaller, just 8 values, we can see, okay, there are some peaks showing up here. So we get some stuff going on. So 16 is the sweet spot for our 16-bit fractional part. All right, and then what I thought, okay, how about we try fast inverse square root, and what we can do, not 4x more work, because you just pick like a more refined value from the table. It's just a one lookup, but you need like 4x the RAM or whatever, if you store it in RAM, the table, or ROM or whatever. Work on the chips PC per percent. No, it's actually, the calculation time is the same. If you have a bigger table, it doesn't matter, but we have quite a limited flash on our like code flash or ROM on our MCUs, so not having, yeah, if having like using RAM, which is like half the cycles, like 1 cycle instead of 2 cycles for the lookup, is a lot, because we have only 2 kilobytes. So that would be a chunk of our RAM that's gone. So what I tried is not Quake's R square root, bitluni R square root, and what I'm doing is I convert the fixed point to binary float, then do the magic number, then convert it back to fixed point and do the iterations. And I'm positive that we can optimize the conversion, since the conversion isn't very complicated. It also counts the leading zeros, which might be complicated, or like might take a long time. If it's not like 1 cycle, it's like then whatever this implementation we got. Either it's a small loop, or it's, I think, 4 ifs in that case, and then a few shifting operations. And we also don't need the sign, because we don't take square roots of negative numbers. So we could basically copy a little bit of that code, extend it here. We don't need a lookup table, and we can basically see in the end if we can incorporate the magic number, like convert it actually to fixed point magic number and do it there. But I don't think it works because it also works on the exponent. So we would like need to do a shift part from the magic number. But yeah, it's only a few operations more, no lookup table. This part stays the same. We don't need to normalize anything. This is also interesting. There is no normalization before and after. The only the part with the normalization happens in the conversion of the fixed to float. I need to turn off Telegram. Yeah, I kept them in there as a sign of respect, because that's quite some research that went into the magic number. So, but what we can do, what I think could happen is if we like resolve that code, that the compiler would be even able to simplify it more if I don't do it myself. Anyways, we have b r square root of fixed point, which is great documentation, yeah. And let's take a look what the results are. So we have conversion into fixed point, b square root, and then conversion back. So the precision loss is basically the same. And if we look at the result, this is the old one. You remember it was like 0.4 roundabout. And then let's do John Carmack's implementation. Alright, it's here, it's the same. And then it's a little bit more. I think it's a few percent. Let me change that. But it's acceptable if you don't have to do the lookup table. The lookup table actually with only 16 values is quite convincing, huh? We could do like a case in the on that. I don't know, or a small look. Yeah, I don't know. Max value, I think. Wait, no. I just removed these limitations so we see what the actual error in the end is. Okay, so actual error is like 5%. Oh, yeah. This is 10,000 is basically our limit of our, like, I think 37,000 is the limit of our integer part. So it's already like 1% around here, but it's all right down here when you try to normalize normals or whatever, directions, converting directions to normals. Yeah, so this is basically what I'm using currently. It gave me a little bit of headache. I had to rewrite some of the code. This is used here. Oh no. I think I reduced the resolution. Yeah, I reduced the resolution. And it's good enough, I would say. We can now take the code, put it, make it distributed again, but only like the whole pipeline, put it in maybe in even workers. You have implemented metallic. Yeah, reflections. We could do even fog now. Do you want to add fog? Fog would really help. Raymarcher task. Okay, Raymarcher fixed point. What we can do is shade, get reflection. We can do mix. Let me check. Return shaded. Mix. Vac. Should we use gray? Yeah, let's use gray. 5, 5, or light blue. 7. And the value is basically T far. Wait, how do we do it? Okay, let's do it like, what's the far value? Check mix. Scale. Okay, yeah. We don't have the division yet, so I actually need to take that 100, okay. So okay, let's see what happens. Did it do anything? Huh? Oh, I need to remove that. I have still some. Oh, yeah, you're right. So the mix is bad. You're right, I'm right. Who's right? Yeah, there's some clipping going on, but what is happening there? Wait, let me check. Oh, wait, we are in the ROM. Eh? Why did we do this? Why did we mix? Break here, return shaded. Far. No. Huh? Seems T is not that high. Okay, let's try that. Nope. Ah. What happens there? It oversaturates. It doesn't clamp. And 5. Yeah, it doesn't clamp. Overflow, yeah. And the sky also doesn't. It's interesting. This is like maybe even. This is the shadow. Yeah. Okay, let me do. And also, I mean, the sky is also not shaded correctly. I would need to sky shade and then do the same thing. But then the shade of the sky is pointless. What? It's always overdriven. Yeah. Overflow. Nice effect though. We could do sky matte. Basically, let's do that. Sky matte color 2. That's our shadow color. We should clip. How do we clip though? Oh, wait, we can do mix clip. We can clip mix. Wait, we can do this like that. No more clipping. At least in one direction. I think it's done, yeah. Is it done? Let's test it with more excessive fogging. Like that. It was excessive. Oh yeah, it's whitening. I don't like it. I can tell you. Let's do sky color. Oh, sky color 0, because that's the lower value there. Yeah, I don't like it either. What is this? It's clipped. It's clipped, my friends. Clipping. Looked kinda cool though. It changed the color. Why is it blue? I'm wondering, why is it still... T... Oh wait, that's too many zeros. Here we go. Yeah, this is, oh yeah, that's way better. Oh, that looks good. Too foggy though. So it looks so cool. Looks so cool. Make a power to vary the fog. Parameter. Make a power. Or what do you mean with power? Parameter. Oh, really? Okay, okay. Power of the distance. So, but you know, the problem is, if you use the power of the distance, then the reflections will look wrong. Because you could reflect a few times and have a different different fog value than you would go like direct length or whatever. So I rather don't want to do that, but I will put it as a parameter here. What is it? 0.05 fix. Boop, 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 boop. Square root. Yeah, and this was my testing. I just noticed that basically the integer part is way too big, and then I tested with stack, call stack, where it happens, and it's always normalized. Laser it's amazing if you get into that. But I will catching up. Why did you? Unshift is ON. Oh yeah, all right. A1K. Thank you for the or how do you spell it? Icon. Icon. Thank you for that. I thought it might be the issue. Required iterating. Icon. Okay. That's a good point. We can try to skip that. So we would do like a push pop maybe. I don't know. How do we? I mean, we can split it. The issue is we won't see anything happening. Maybe we need to implement a priority. Yeah, I didn't check it in. Here is the tasked version. Performance didn't show me. I thought also that it might be the array functions that are slow. And this is the same version without tasks. And it's done. It takes only like 1.5 seconds or something. So not using and we moved on. We don't want to split into so many tasks, only one task per pixel. And this is fog. Ah, you did it in multi-threading. Ah, it doesn't load. I will check in my latest versions, so you will have 3 different. Yeah, I'm doing it now with fixed point math because I was stupid. I need square root anyways, so I can do basically all the pipeline of one ray within the MCU. So the communication will be lower and we just do per pixel Oh, it includes icons fix. What is icons fix though? What did you do like to improve on the shift? Yeah, yeah. I will check in a second. Okay, I have something on my stack. Let me. My mind stack says I need to do the fork. In my design, each MCU will calculate 1 pixel, and then I think, okay, this looks good, so I can check in. Alright, so this is fixed point math. I had to scale down by like 10 all the things by 10 because our integer part is too small of the fixed point math. But I will check it in. Okay, here we go. And I also give you my square root tests. 3 versions. Oh yeah, I need to pull first. Wait, no, I can sync that and then incorporate it. Okay, here. Sync. You will get the latest fixed point version as well. That are just 3 different files. And then the tests. Okay, now let me check GitHub. Get so many tasks, issues. Where is it? Yes, 16 by 16. Issues. Edits. How do I take it? How do I pull it? Huh? Don't understand how that works. Wait, I have to like take the code and then maybe you can make it a pull. Oh wait, that's the wrong file anyways. I need to put it in the other file. Let me just copy it and then I will incorporate it and then we can close it. Because I changed, like I copied everything and removed because there was like the code parts that were used in the regular marcher and the task marcher, I just moved them. So here, where's this? Unshift. Okay, here we go. Let me paste it. Yeah. Bye, Jumbo. That's minus minus. Here we go, plus. So you made basically the inverted the direction and then pop it first. Oh yeah, that makes sense. So just using as a stack, because the higher priority will happen first. Okay, execute, wait. That's the part with the tasks. Scheduler. Yeah, it's not impressive. I mean, I did my ray tracer on the ESP32 runs in real time, 320 by 200 or something. Oh wait, I destroyed it. Must concentrate. If priority. Here we go. This is that was C++, yeah, but this is also compiled. Chrome just does like a okay, and this is execute pop. Let me run that. As my code here. I would need to merge. Oh! What? What? This. Johnny, this ball is pink. This is way faster. Okay. Now we need to transfer the pipeline. This is really substantially faster, really. That's not bad. Especially it's make it 4K. Yeah. I like that. Yeah. Yeah, it's because of the HDR display that it looks a little bit reddish. Okay, so commit, and then I will just take the link. Close issue. Thank you. Closed. All right. Thank you very much, Icon. That was iconic. All right, here, synchronize the changes and Oh yeah, the canvas element. Here we go. Uh, Sorry, I was just busy trying to finish my mental tasks here. That's the resolution. If you want 3000, hmm. Yeah, we can close that. We would need like to also improve. Okay, new things that are added. Yeah, my CPU is bad. It's old now, and it's not a Threadripper. We can do it now multi-threaded. Wait, let's check Sonic's implementation. Did you use worker threads? Why doesn't it open? Stupid. As soon as we incorporate the new renderer into the worker tasks, or I mean in the tasks, then we are way better. I also need to unify the rendering again, because the shadow calculation is not that great. Wait. Code. My brain was stuck for a moment. Wait, it's calculating. Oh, I see that. 100%. Oh no. Oh, it's done. It's done. I guess it's done. No, 70%. Oh wow, CPU is quite busy now. Worker.js, you put it basically in one. Three times as fast. All right. Oh yeah, I see that. Lines per worker. Yeah, and everything else is the same. You just copy the whole code in the worker. Alright. Yeah, this will never finish for me. What resolution are you rendering there? Mister? Oh. 100%. Wow. Oh, full screen. Oh no, I hope I didn't start it on my main screen, 4K. We will see some frame drops. Uh-oh. Browser zoom level. I have probably zoom level, but not on your page. Oh no. My... let me check. Where is the resolution? Event data, lines per worker. I can't tell. Canvas. $3,360. Oh no. Yeah. That will never finish. I would just need to restart it. Okay, you know what? Let's do that. Oh yeah, that's a better resolution. But let me start it on a different screen here. This one. Oh no, this is also. Yeah, this is this. Then what? All right. No. Okay. Too much. That's too much, my friend. Can't do that. Okay, my goal. Put our new raymarcher, the integer raymarcher, which has quite some overhead to ensure. I had like to make sure that I'm not working with numbers. I also changed. Oh no, this is the fixed point. I also changed here int array 32, and I also made a sub e and add e, which basically clips it to 32 bits. So if there is any effects of numbers, they will be nullified. I think we can do is put everything in, merge it with time. Hey, Fego. And there will be only one task or two. I mean, we can do. I can do a worker.js. Let's test it. And since we can calculate the whole pixel on the MCU, it will be way simpler than working with the test. All we did on Monday is this is throwaway. So, what do we need? I just copy the whole file and remove everything that's not needed to calculate. Okay, I don't need that. I don't need that. Init objects. Maybe we should make the whole object in a scene. Oh wait, I should do it first before I convert it. You know what? Let's remove this because I want the data to be transferable. We have also the image data. How do you how do you communicate that? Over message loop? Like, do you give it the data object, or do you return like pixel values? Oh, it's serialized. Okay. Yeah, no, then I won't do that. I will just... I can close the tasks here. I moved everything, objects. This will be class scene. I hope it will be serialized as an object. Const, these are okay. Oh no. It's getting too object oriented. It's getting too object oriented. Because I want to transfer the whole scene setup. I don't want to initialize it on each of the devices. Can you serialize objects? Maybe I'm doing too much here. Let me check. Yeah, we can check the scene. Constructor. We can move everything there. This is the const static. Wait. It's just the static, I think. But is there a static const? Yikes. Oh no, I hate it. Static getter. All right, okay. So it has to be like that. Which matrix? What? 404. What? We are not rendering it on a matrix. It's only calculated on these things here. It's 4 by 4 by 10. It's a volume. They can. No, yeah, the cluster is just for calculation. It will communicate over serial to the PC. So, if you missed that first part, here, this is an M.2. This is a serial chip here. This is an RISC-V CH32208, which controls these clusters, 10 of those, which carry 16 MCUs. So it's 160 MCUs. And we have to transfer the data over serial. So the calculation, it's just a demonstration project. We put this in a mini PC, and this will be the accelerator for ray tracing or whatever we implement there. Yeah, yeah, very confusing, very confusing. It's just a supercomputer on an M.2 supercomputer. Yeah, yeah, basically, it's just a demo project to that we can run or demonstrate that it can actually work like that. It's probably faster to do it on the CPU with floating point or even shaders if you like than on that. But I think my mini PC isn't very fast, so oh, they are CH32V003. So they are really small. They are 48 megahertz, so not very slow, but they have only 2 kilobytes of RAM. So we are at the limit here. I think it's only 2 kilobytes. QFNs. That's the QFNs here. The QFNs are way better, smaller, 20 pins each, and yeah, quite teeny tiny. Yeah. The old ones, the TS SAW, these are those here. Yeah, I made clusters like a few years ago. Sub 8. Yeah. Are you trying like to use the fun what is this CH32 fun repo from Charles? He did a lot of cool things for those tiny. You can even emulate USB. All right. Time for mega cluster LED wall. Yeah, one LED init objects is now seen. Wait, render. New scene, and here we go. How many LEDs? Or I did Charlie Plex for 15 by 16. That's also the same MCU. Works totally fine with even like 10-bit depth of whatever. Or like this small device doesn't use Charlie Plexing and has sound, everything. That's also working with those MCUs. They're really cool. Can I turn it on maybe? Oh yeah, you can use Charlie Plexing for that. It's a little bit more complicated, but you'll figure it out. And this looks so cool. Like Charlie Plex, you just sacrifice one row. You can use, how many pins do I use there? Yeah, I use, I think 16 pins. You can do n times n minus 1. The LED pitch, I don't know, 2 millimeters. It's a cool mini device. I can give you the link to that. You can watch the video on that.
Today I wanted to show you this mini console that
it also, the video also focuses on fast display. Yeah, you can watch. Here's for the others as well. You want to watch the. I don't know if I did a good job explaining it there, but basically you can drive many frames per second if it's not color. But you can also use like the really tiny addressable LEDs, SK28 whatever, if you want that. All right, okay. Good. So then let's continue here. Scene. I have something in my clipboard. Oh no. Shoot. Yeah, all right. Yeah. I destroyed. Here we go. We just need to pass the scene to each of the functions that care. This is annoying. All the objects. Okay. Scene, we can serialize it afterwards. I'm wondering if, wow, there's so many parameters. Sending it to the MCU. I will put this also on the MCU first, and then later we can send it to the MCU if we can like do a serializing implementation here and deserialize it on the MCU or all the MCUs to have like a random scene or whatever. Each frame can have a different like positions or whatever. I don't know. Okay, so we can test what's here. Where's the light position here? Oh yeah. We can do scene first. All right. Stack is blowing up. S in shadow. Yeah, we need scene here as well. S in shadow. Get light position. Material is here, alright. SDF. I think that's it. It will not work. Oh yeah, by the way, all the constants also in there. I don't know if we want to go there like that. Far EE2. Okay. Where is the E? Oh no, case sensitive. Get normal. Yeah, I mean epsilon shouldn't be there. But with the fog, I'm not sure about that. Also far. This here, I don't see it. That shouldn't be changing. I don't really want like to pass thousands of objects blowing up the stack on my mini MCUs just to have epsilon. Whoops. Far. Yeah, far is here. Get reflection. Scene. But this was in the distributed. This is also implemented different way. Let's keep it like that for now. What did we use for SDF? Oh yeah. Yeah, this is whatever. This should never be called. Okay, far SDF scene. Far break. All right. That's manageable. Fog. We can do fog also a parameter. Doesn't look like it should have that high priority. And shadow, then reflection. All right, that should work. Probably not. Here we go. What's scene? Yeah, we're not passing it to SDF. Not this SDF, different SDF. Oh, yeah, all right. Wait. No, this is object SDF. This is a different SDF. We're testing only SDF of the object. Here is scene. And here as well. Oh. So scene is empty, no objects. Let's see if we have dark shadows, yeah. Yeah, I need to put a breakpoint here. Okay, we have the object. Okay. SDF seems to have the objects. The only thing that I don't see we can do that. Eh? Ah, here we go. This one is missing. But where is object I coming from? That shouldn't exist anymore. Or is it like sphere is not ping? Okay, I will change that. What's the mixing colors for pink sphere? Red. Then we have a little bit more blue. That's like 7, 5. Here. Here's your pinks. Didn't work. Huh? Oh, far is undefined. Did we remove far again? Static far, okay. Okay, you know what? Fuck this. I'm putting far as well here. Sonst. Okay. Yeah, we need to put it in a getter, like a static getter, and no way in doing that. F off. Bastards. Okay, here we go. Pink sphere. Oh no, pink crash. Huh? Well, sky mat is from objects. Here. See. Hey DFGA. Here we go. Boom. Is it pink enough or is it too gray? It's pink. All right, here we go. Now we have pink with some reflection. Wait, was it? Uh-oh. It crashed. What's light position? Okay, seen light position. A few more spaces where sky matte color. Okay, again. It's not very pinkish to look at. Let's make it less reflective then. Yeah, we have fog now. Yeah, because of the blue that it's reflecting. So we reduce the reflection from half to 2 as well. Now it will be boom. Good enough, close enough. HDR next. What's HDR? Oh, looks pretty good. I'm wondering. HDR. Something stopped working here. Just an app closed. I don't know what's happening. Oh, the Explorers. Something's restarting. Huh? I don't know what's happening on my PC. Someone's trolling me. Hexor. Some Hexor's trolling me. Oh, high dynamic range. I mean, it's already high dynamic. This is the reflections are high HDR. The only not non-HDR is this here. Can we have an HDR canvas in JavaScript? Wait a second. "2D canvas HLG." GitHub. Yeah, that's probably okay, let's see. But how does that work? Ah. Too bad. What should I look at? Google. Oh. Oh, HDR environments. All right, all right. Okay, the last conversion. So if anyone wants to do HDR, I know there HDR is possible in browser. You can probably do it somehow with GPU or whatever already now. If you want to do it in still hard. You need a video, HDR video. You can do oh, what? I'm recording. Why am I recording? I pressed the wrong button, it seems. Okay, so if you want to do here's where HDR happens. This is where we lose our fractional part of each. For 8K HDR 3D 240 FPS. So the color is still there. We have like 16 more bits of resolution. We have 8 bits. The higher bits 16 to 23. Color to 255, 0 to 255, and then we have like 16 bits of fractional part, which actually could be a HDR. Very simple. Just need to substitute canvas for something that works with HDR. Or you generate a PNG, an HDR PNG or something. HDR image, I don't know. How do you image data? Yeah, image data is but I'm wondering DCI3, that's like a white point. gamut. Okay. All right. Yeah, that's up to you. I just commit the new change. Oh, the worker doesn't do anything, but we can do this for now. And this change will be or it's 3D decelerator. Yeah, it's what we have right now. Huh? How do we push? All right. Custom HTML5 can. All right. So this is not my goal. I will do the fixed point. I will put everything into a worker that's necessary to do worker stuff. Okay, sky. Yeah, we need to have the implementations of the SDFs. That's alright. Collision, render object, power, 16th power, calculations, vector, add, sub, square root, that's proven to work. Render, we don't need to render though. You can see what ChatGPT generated here with spaces. Get reflection is basically what we do. This is what we need. Get light, get normal, SDF, and scene. Oh, wait. No, we don't need that. Scene will be passed. This is, yeah, we can just comment it out as a reference. Image data we don't need. Yes, all right. Image data context canvas. All right, here we go. Now, how do workers work? Message loop. Should copy your code, Sonic. Web workers. All right. Okay, new worker. Blah blah blah. Post message. Yeah, but how does it look on the worker side? Import script. Wait, what is this? This is how it looks like. On connect function event. Okay, let me check your code again. just steal all your code. Oh. Okay. Okay. Structured clone algorithm. Getting a dry mouth. Okay, let me do ChatGPT. And we need also to copy that code. I know you hate having a copy of everything, but I want to delete stuff. Oh yeah. Tasks. It's a different version of tasks this time. Okay, what I want to do is scene and an SDF. Wait, we can keep some math here. Get light, reflection. Oh yeah, we need to keep render. Scene. Yeah, we can remove that implementation. Oh, we can keep it. Now we have it in fixed. We actually don't need it here, but I will keep the math. We can maybe... I see the problem as soon as we use web serial, we can't include external JavaScript files and so on. So that will be an issue with trying to include stuff here. Okay, vec fix unfix small ed floor blah 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 render object. Yeah, material render new scene. Okay, we just removed some of the stuff. We don't need everything there. We can be thorough and remove everything that we actually don't need. We might don't need most of the math here. Would be interesting to see like the split. Okay. Okay, let's chat. Let's vibe code. Threaded. That won't work. It didn't work before. Like, I mean, I tried to get a proper tracer from him, but On message. Okay, this is what you said. We can do that. We don't need on connect, we need on message. Results. Okay, the serialization, we need to check that. Oops, here. This will be the message. Color. Him, her. It is. Yeah. Nobody cares. Except me. Post message color and scene basically. Wait, the message came from. Is it like just web worker, post message and data? And data. Yes, we will see how far we get with that. We also want to put okay. I have an idea how we will do it. We will do it the same way like we did in the tasks, but we will create a task per pixel, or we can create, you know what, we can make it faster by only creating, oh no. We can complete the tasks. How do we do it? Okay, we will see. Above B dragons. No, I do 160. We need to simulate our MCU. Now, let's make it a variable count of workers in the end. All right, so this is that. You know what we can do? We can do we can flatten this loop basically. Der Hammer. Yeah, that's why we probably used to it like that. On message. Oh yeah, I need to put that somewhere else. Wait. Web worker and here. Wait. Worker on message. Workers. Worker on message. Terminate. Do I have to set this function every single time? I mean, we can just set any function there on message. All right. Okay. We will do as follows. To 16. I think 8 cores, so let's keep it like that. Workers, and then do they start at the event loop, or why is it attaching? I mean, it attaches. Oh, we post a message. Okay. Don't I set them on message? So multi-threading. If this actually starts the thread right away, not on the next. Yeah, I know, for the return value, but if you post the message before, you have to like attach the message for the return value before you start the task. Or is it starting the task in the next event loop? So that's one issue that I see with that code. Yeah, I attached before, yeah. Oh wait, I should const worker equals, and then I have still something on my stack here. The stack is this. Oh yeah, we don't need that. Function what is the data? Or is it an event? Event as well, okay. Work are done, so we have. Oh! We need to pass the pixel as well. Okay. Just like we did on the task thing. Yeah, I just need to return one vector, so that's alright. Yes, it does. So we could actually convert it to RGB, so we don't need like to pass the object, but I will start simple and then optimize later. Function first, people. Function first. On message. On message could be also crash. Worker. So who knows what happens? On message. Worker terminates. Oh, we will create a new worker every single time. We could do the same, use the same worker to do the next part, but we will start like that. Optimization later, okay? Result lists. Okay, yeah, that's what's happening there. We need. What does it mean? Didn't remove the worker, terminate. Maybe we should check out what worker does. Workers API start worker example. Oh, come on, where's the specs? Web workers. Yeah, W3 schools is not that great. Okay, terminate and post instance method. There are not many things. You probably need to remove it also from the array or something. Kept alive, yes. We can basically keep it alive if. But does. Oh, alright, interesting. Yeah, we will start with a smaller image and then try improving later. Step by step, friends. Let's do it. Okay, so. What do we have here? X, Y, and everything else is and then okay, so then do whatever. Loop. I have too much open tasks. ADHD is hitting hard right now. Okay. Worker. Morker. Message worker done. Okay, you know what we can do? We can do a function here. Function next pixel, which returns something or null. So worker done will be basically, let's take it over here. Let's take it here. So next pixel will basically fetch let's do return now. If it's done, no more pixels. And in that case, or if not pixel, worker terminate. Otherwise, this is like pixel. That will be pixel next pixel, and that's it. Oh yeah, in that case this is just copy paste almost. All right, doesn't matter if we do it there. This is our loop, which will be this part. This part is happening here and there. Let's destroy it here and work out done. This happens here. Color, color, color. Blah, blah, blah. Was it message? Post message. And then pixel. Then we need to construct pixel here. xres. Now why I do all those calculations here? It's just for the field of view. Am I still streaming? I hope you're still there. Yeah, scene, basically we have that. We need to camera position. It's still there, this text. Origin, thank you. Origin. Then we have deer. We have scene. Oh, I think I need to do it like that. Why is it called? Oh yeah, here, scene. I don't need that. That's just for JSON. We'll do it anyways. RD, and then we need X, basically X, Y, Y. Okay, and depth. This is then let return pixel. So, and now we need to check if I will tell you, this is coming now. This is coming now. That's how. And now we have here we go, electron hash. Okay, so this is how it iterates. It starts at 0, so this is our loop, and it goes through the size, and that's basically it. Put image data, we can do this like we can do it every pixel, which will be annoying. Okay, or we do it like that, or every line. Yeah, we can do it every line. It's just to have any update here. Workout done, next pixel. No. I just make worker count, and then in the beginning we will do worker push, worker done, and what we do is we create workers that will start with the pixels, but we need also to create that, to start that, and x starts at 0 and y starts at 0, and they will basically start with the first pixels. Oh wait, after the terminate, else not pixel. Okay, here we go. This is how we do it. If why are we so negative? If pixel, do it, else else terminate. What? Okay, and the same as here. Since we could have less pixel than workers, we start like that. Hey Cooper. Crypto miner. Positive condition. Yeah, start with the positive and then the negative. Like you always said, if arrow then go to, and the go to was somewhere on the bottom of the basic file. Also the evil go to in C++. This is crazy. Yeah, they're global. For now. Okay, we can call it pixel or render. This is too generic. That's too generic. Oh, we also didn't set the pixel when we return. That needs to be fixed. So when we get here, oh, data color. Okay, so we need to return, and we need to also get xres and then x y This is somehow maybe event loop. I mean, this is handled like when the worker done. This happens. This is a message. This happens in the message loop. So the main thread only executes one message at a time. It's not worker done doesn't happen at the same time. So there is no issue with that. The interface is the message loop. That's why it's so strangely implemented. we also need to store in the worker thread, we need to store the stuff that we put in pixel. So, oh yeah, this is set correctly. Then the pixel stuff here. All right, we are almost there. This is just our reference. And then we do color, and then we X a data. Why? Fucking autocomplete. I hate it. I want a small e. Ah. I don't want you. It's enraging, just as auto-completing braces. X. Yeah, sorry. Please, no timeout for me. I copy that. I can't, how do I do it? I have to press escape to not have my code that I typed intentionally be replaced by something else? That feels wrong. Win-word. Re-return X, Y, and color. Does it work like that? Does it just render now? Crash. What did it do? Cannot be accessed from origin null. What? What's that? Okay, time to install Firefox. But this won't work with... But we are so secure now. This is just like the pop-ups for accepting cookies. It broke. Does it run in Edge? Maybe I could run it in... sorry. I'm not seeing it running on any... It seems I have Firefox already installed. Yeah, I have Firefox. Yeah, you just break it. Not now. All right. Let's start with this one here. Boom! Oh, interesting. Can we put this here? Here we have H. Okay. Next pixel, yeah. What value? What do you mean? I have a type next pixel. Where's I missed one W here. H virus. Oh yeah, scene wasn't a global variable. We need to pass it to. Oh, we need. So. I noticed my mistake. Ah, come on. Renderer scene. Renderer scene. I give up. Okay. What now? Course error. Rendre. Rendre. Wait. Render Y. Render. Where's my next pixel? Next. Render Y. No, that's correct. Has nothing to do with that. It has to do with course. So actually we can do the following. Wait, where is it? We can just copy the whole text, which is stupid, and use these here. Yeah, this should work on any PC, not only mine. That's why I'm not disabling this. What, blob? Oh, interesting. Yeah, we can just use the worker code and then here. Wait, what? Worker URL. Okay. Yeah, that's also what ChatGPT suggested. Dieses. Yeah, source code. Yeah, but look at this string here. Yikes. Okay, worker.js. This is terrible. I hate it. Okay, find a better way and tell me, please. I'm open to it. So, blah, blah, blah. Worker. What? What do you... Seriously? I really need to... Oh, man. Yeah. Void. That should make it complete. Where is it? The renders, the stray render scene here. Ah. That's cleaner. Oh! What? Undefined. Oh, actually that worked. Origin is undefined. Okay. Origin. Wait, we can check the stack trace. Call stack. Oh, shit. Yeah, my bad. Yeah, my bad. Sorry. Origin. and I renamed it here. Okay, here we go. What? It only stores data, not the functions. Okay, we're almost there, almost there. Oh no. Scene, all the stuff recursively. We have like the objects. Structured clone. Yeah, fuck. We would need to recreate the whole scene just for each pixel. It's no good. Damn. No, that's yeah. I would generate the scene, but we need a better way of serializing and deserializing the scene, and also like the objects and so on. Oh no, this is like double dispatch or something. Oh, I hate it. Let's make a new scene here. F this. It will be the same thing, and fix E. No wait, vec E. At least we can do that easily. And have this scene. Color needs also deserializing. Here, because we use color clamp stuff and oh no. You want to see, basically, you want to see the success? Here we go. No success. Scene is not defined, huh? Not defined yet. Or what's the issue? Okay, okay. All right. Good night. Oh, it's late already. I really wanted to do something on the hardware today, but won't happen. And next stream will be next week. I can't do because I have guests this weekend. I need to clean up. I can stream on Friday, unfortunately. Okay, so we need to initialize the scene afterwards. I really don't want to do the scene stuff. Let's do it here. Does that help? Oh! Oh no, this has to be in order. Kidding me? Wait, vec3 is... Can't access before initialization is the error. So how do I solve that? Let me check this call stack scene. All right. Yeah, the order. That's strange. Okay, yeah. Different rules, my friends, different rules. What now? Spread syntax requires iterable symbol iterator. What? Oh yeah, that's missing a V. V. Okay. Oh, that's not a... I wanted too much. It's only depth. That's not... Here we go. What now? Eh? Assignment to constant. Oh yeah. Fuck. My bad. I'm so worn out from this project, I can tell you. Why do I do such complicated things? I could have completed the video like a week ago or 2 weeks ago with just calculating a hash value, and that's it. But I want a ray tracer going 5 extra miles. Or 10 extra kilometers. Here. What's next? Oh yeah, e-worker. We don't know worker here. What's in E? that a worker? Origin. Is this the worker? Yes. Current target. Wait. Didn't we have the example here? I need to check. Oh, it's using that. Okay. Cells. Did you put them in the... Oh. What? That works? YOLO. What? Yodel? 8 CPUs. What? Nice. Let's see unsere Leistung. Let's see Leistung here. And yeah, it's always busy. Ah! Yeah, more pixel. We need more. More pixel, people. Okay, give me the code. Give me the code. We cheated a little bit, but here we go. Here we go. Ah! 4K resolution. Full utilization. Okay, I'm streaming at the same time, and recording. How big is this image? At least we can see the progress. Should I check in? But then I will remove the worker file. The worker file doesn't do anything here. Remove the recycle bin. Here. This is now tasks, commit. And push it. Here we go. You can enjoy it. And this is still calculating. This is beyond the fixed point precision. You can pixel peeping here. What is this? You can see the resolution of the of the fixed point arithmetics. What is this? What is this? You can... Ah, this is cool. Here is where the shadow starts. Oh, we see the reflection. And here the limited precision. Oh, this image is so huge. This is amazing. Here's the box. And we can see reflections. Okay, some artifacts, but oh well, it works. Distributed. Here we can see the complete scene already in the cylinder here. Some bending from the fog. Nice. I'm wondering how fast it will be if we run it on the 160 FPUs, MCUs. Oh, we can see errors here. There is some rendering errors already. Yeah, I don't care. Try it on Firefox. Okay, wait, we need to finish it first. Wait for it. It's so cool. These are that have been like 2 coding sessions only. We did nothing hardware related. Look at that. This is a perfect square. Here. The floor needs some leveling. More CPUs. Yeah, I only have 8. Here, look at my main PC. Yeah, we need 160 MCUs here. This year, 160 of those. I will put it in C++. This will go real time. Oh, still calculating. Almost there. Here we go. And they are gone. Look at that. The web workers are gone. My code worked. Okay, now Firefox. Let's see if Firefox actually does something. It's not faster. It's slower. Maybe I should update my Firefox version. This should be like a super old one. Yeah, no, this is not faster. Okay, let me kill it. Oh no. How do I stop it? Okay, let's not do Firefox anymore. Yes, it's committed to GitHub. Oh wait, did I commit with the big resolution? I hope. i3? What? Whoop! Which resolution did I commit? I hope it wasn't... Yeah. Oh no. Wait, maybe I should do a bigger resolution here because we can see. So let's do 640 by 360. Okay. Updated. I guess. Oh, yeah, I can remove stuff that we actually don't need from here. Let's do the maintenance here. Okay, we need scene, we need sky, we need that, materials, planes, cylinder, box, we need all that. We need that, we need all that. Okay, we need all the code. What we don't need is here. Wait, we don't need all the math here. We don't need shade. It's odd. I really... We don't need shade, don't need shade, don't need shade. Don't need SDF, don't need SDF. There, we don't need collision. Okay. Alright, I guess I have to update my Firefox then. If it's because it looked slower, we don't. I actually don't know what we need here. Ubuntu. Mol-I. Benchmark, yeah, we can benchmark it. Vec I to string real. I think we can keep the math here. Even though, we will have some bad time here. Square root. We have some normalization here as well. Oh, there is some bad time because I missed a few plus and minuses here. Sub. We need to do individual. Anyways, some copy paste code. Square root, reverse square root, I. Yeah, I don't care. Bin float, blah blah blah. Render. Okay. Does it still run? Nope. You know what? I reverted. I don't know what's going on. I just keep the same code there. Okay. More web workers. Oh yeah, how many? Can we see how many cores you got? And creating. Okay, you know what? I do the following. We simulate now. Yeah, it's 8 for me. Let's look at that. Look at that. That noisy little. This is cool. Okay, it didn't update everything. 160 cores. Oh, it's 11 o'clock. I will go I will go offline right now. I will update the code, the latest change with the concurrency, like how many. I leave it like that, just as a hint. And update that. Sync that and have fun. I see you next week. By then I really put it on. Now that everything is working, I really put it on an MCU. I will test it. So maybe I will point out the stuff that I will go. So next steps to do is USB CDC on my programmer board. So CH32V208 and make a renderer on 208, communicate with browser, render tasks, and then the next step will be proceed to forward to node 3s. Okay. That's just an intermediate step will be to run it on the MCU, just one thread at a time, and then let the MCU. Okay, so basically okay, that's the steps that I will do the next days. And if there is a major result, I will update the GitHub repository. So, good night, everyone. Have fun with that. See you next week. Bye bye.